Now we're going to the uniform distribution, one of my very favorites. Okay, so I want to give you a little sense of how the uniform distribution looks. Let's see. Here we go. We're going to get uniform. Boom. Okay, uniform. That means any of these possibilities can happen if I take a sample. So let's see what I mean. I'm going to take a sample of 5 different values from a uniform distribution. Okay, so let's take a sample animated. There. See, I got somewhere down in here, I got a sample here, I happened to get kind of a clump up here, and actually the mean for that ended up right around in here. Let's try taking, let's clear that and just see what happens when we do it again. Oh, okay, now the mean ended up here. Look at how they kind of clustered out. It can actually, I can pull equally from any area here. So I can try it again. Okay, and again. You can see it can land anywhere. It has this equal probability of landing way out here on the edge as it does in the middle. That's quite different from the normal distribution. Look at now watch what happens. You'll see things seem to clump around here. There's not as many selected from the edges. See, there's one, but it was pretty close to the middle. Huh? Yeah. So it seems to clump up a lot more as far as how this works. I do want to show you something kind of interesting. Let's go back to, oh, you know what? First we're going to, let's do anything we want. We're going to have this really, that's total bizarre distribution, right? So let's see what happens when we take a sample from it. Okay, we take a sample, boom. Let's see what happens if we take 1,000 samples. Wow, look at that. A totally bizarre distribution, but hey, this actually looks almost like a bell curve. Is this weird or what? We get a bell curve that comes out of a bizarre distribution. Let's see. What happens if we try a normal distribution? Let's take 10,000 samples of it. Wow. Another bell curve. And this bell curve is like tighter than the original bell curve. And that's the sample. That's the bell curve of all the samples. So we get something, let's see, let's try a uniform. See what happens out of that. Whoa, again. It starts approaching something that looks like the normal distribution. That's like totally interesting. Okay, let's try. Look, total bizarre, strange distribution. Take 10,000 samples, look at the mean, and it starts looking like a normal distribution. Order out of complete disorder. We're going to see some very interesting results that grow from that. But for now, I just want you to keep in mind this is what's going on when we have random samples from a uniform distribution. It can just means that sample can fall out from anywhere. So for the uniform distribution, we've got expected value and variance. The expected value is given by this. You can just add up all your different x's, divide it by the total number of readings you've taken, so to speak, and here's how you would calculate your variance. So that's all there is to it for uniform distribution. Now let's go ahead and do a problem for the uniform distribution. In this particular problem, we have an employee is selected from a staff of 10, and they're going to supervise a project by selecting a tag at random from a box containing 10 tags numbered from 1 to 10. Find the formula for the probability distribution of x representing the number on the tag that's drawn. What's the probability that the number drawn is less than 4? So this is pretty clearly a uniform distribution. The probability that you're going to draw any tag is going to be 1 out of 10. and that is for x is equal to 1, 2, 3, blah, 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 all the way up to 10. So therefore, the probability that x is less than 4 is going to be just the summation of all of these from 1 to 3, right? Because it's less than 4. All of those probabilities, and that is simply 3 out of 10. So this is another one of those ones that looks like it's really confusing when you read it, but when you actually see how to work it, it's very straightforward. Okay, now we're going to go to the exponential distribution. And by definition, the exponential distribution is just defined to be 0 for x is less than 0. And for x is greater than 0, we have f at x is just lambda e to the minus lambda times x, where lambda is a positive parameter. But what is that exponential distribution? As it turns out, it plays a very important role in a large class of problems that relate to what we call the lifetime of any particular item. So for example, we can have an electronic component and it's known to have a lifetime of, say, 10,000 hours. So that means that the component is expected to fail after about 10,000 hours of use. But of course, this is just an average value, and some components from the same batch will last less than 10,000 hours, while others will last longer. So the lifetime of a component is just a random variable. The memoryless property is just that, well, some of these lifetime problems exhibit this memoryless property. And we can consider a very large number of identical radioactive atoms and observe their decay. So for the first, however t seconds, a proportion p of those atoms is going to disintegrate. If we leave the lab, come back later, there's going to be some atoms that haven't disintegrated yet, and we observe again for another t seconds. And during that time, the proportion of those atoms that disintegrate is also going to be p. And here I just want to give you a little sense of half-life. Okay, we're seeing radioactive decay here. The red dots are a large number of identical atomic nuclei, each obeying the same decay law, and we can select a mean lifetime of the nuclei with the slider, right? So we can make it, I don't know, we'll make it 42 seconds, something like that. And then we press the start button and watch them decay away. The green is the number of nuclei remaining at any given time. And we can see it follows this half-life idea. There we go. And we'll do it one more time. We'll make it even a little faster this time. Start. Ooh, look at it. They're dying. But at any given time, the same ones would die in the same way again. Now we'll translate these observations into the terms of probabilities for individual atoms. We can first state that the probability for an atom to disintegrate in the first t seconds is just p. And we return after s seconds, and the probability for a still not disintegrated atom to disintegrate within the next t seconds is also p. And so the probability that an s second old atom will last another t seconds is the same as the probability for a new atom to last t seconds. This actually does, if you think about it, it all makes sense, or you may already know this if you're familiar with half-lives, it's as if the atom had absolutely no memory of how long it's been around. For radioactive atoms, there's no aging. As long as such an atom remains alive, it is absolutely identical to itself, and then, without warning, it decays. So, a random process is called a Poisson process if an average of lambda events occur per unit time or unit space, and it satisfies that the number of random events occurring in any segment of time or space is independent of the number that occurred in previous segments. It's called the memoryless property. So the average lambda is a constant, and the smaller the segment of time or space, the lower the probability of two random events occurring during that segment. So two or more random events cannot occur at exactly the same time or space. And then we can let the discrete random variable for a Poisson process be defined as follows. I'm going to do it in two different ways. I'm going to first say that it's x is going to be the number of events that occur during a specified time t, and next I'll do it for a specified space y. Copy each one of these equations down because they're crucial. Sometimes I give time problems on quizzes, sometimes space. So I want to make sure that you understand how to do each one. Here, the probability of an event occurring during some specified time is lambda t raised to the x e to the minus lambda t over x factorial, and then that's for x is greater than or equal to 0, or 0 for x is less than 0. And the probability, okay, now this one is for space y. Probability of some event, or some number of events, is lambda y. Notice here we had a t, now we have a y. Lambda y raised to the x e to the minus lambda y over x factorial. That's for x is greater than or equal to 0, otherwise it's 0. Oops. For x is less than 0. So these are absolutely crucial. Be sure you've got these down in your notes. Now we'll go ahead and calculate a problem. We can say that a computer network receives an average of 0.1 messages per second, and it's a Poisson process. Determine the probability that the number of messages x during a 50-second interval is equal to 7. So if we do that, use Poisson, and we're looking for the probability of 7 messages. So say lambda t to the x e to the minus lambda t over x factorial. And so that's just going to be, well, let's see, lambda, we're told it's 0.1, so it's going to be 0.1 times, well, it's 50 seconds. So times 50, and raise that to the 7th power, e to the minus 0.1, 50, and then divide all of that by 7 factorial. And when you calculate that all out, it becomes 0.104. So that's the probability that the number of messages is 7 during a 50-second interval if we've got a Poisson process with a lambda of 0.1 messages per second. So now let's go on a little bit, and we'll say that the expected value and the variance for the Poisson distribution are given by expected value is just lambda t. So, and I always like this one, you know, because it's like so simple. The variance is also lambda t. So you can't beat that for simple. Now, let's go on to another problem. We've got 2.7 calls coming in per minute. Find the probability that fewer than 2 calls come in any minute, or more than 10 calls come in any 5-minute period. So for the first one, fewer than 2 calls come in any minute. Well, that's going to be the equivalent of saying the probability that no calls come in plus the probability that 1 call comes in, right? That's the only possibilities we have that are less than 2. So we can say that's going to be e to the minus 2.7 times 2.7 to the 0 over 0 factorial, that's the probability of 0, plus e to the minus 2.7 times 2.7 to the 1 over 1 factorial. And when you add those both together, you will get 0.2487. So that's how you do the first. Now, the second is more than 10 calls come in a 5-minute period. Well, we can say that it is going to be the same as the probability that x is greater than 10 is 1 minus the probability that x is less than or equal to 10, right? So that's going to be 1 minus the summation. I'm going to be very bad here, and I shall write summation from 1 to 10, or 0 to 10, of e to the minus, well, let's look at this, lambda times t. We can say that lambda 2.7 times 5 is going to be 13.5. So we'll write this out as 13 minus 13, whoops, 0.5 times 13.5 to the x all over x factorial. And if you work that all out, it is 1 minus 0.2971, which is 0.7129. Voila! And there we go.